Hello everyone, good evening. Let's wait for 3 more minutes so that other students can join, and then we will start today's session. This is week 2 problem solving, right?
So week one we only upload, sir. Week two only not uploaded.
Yeah, this is week 2 problem solving. Like in today's session, we'll be solving.
Okay, sir.
Yeah. Okay, I think we can start today's session. So, let me introduce myself. My name is Arpit Bal, and I'm a PhD scholar at IIT Bombay in Department of Electrical Engineering. And I'm also a PMRF scholar, and I'm a PMRF TA for this NPTEL course, Digital IC Design. So, in the previous week live session, what we did is we did some numericals related to VTH variation with VSB, and we also did some numericals related to channel length modulation. Then we did a few numericals in which we had to figure out what is the region of operation of NMOS and PMOS, and we were supposed to figure out what is the drain current using the unified current equation, right? That was all about the week 1's live session. So in this week's live session, what we are going to do is, okay, let me add the students. Okay, so in this week's live session, what we are going to do is we are going to solve a few numericals which takes into account one more short channel effect that is called as DIBL, and we will solve few numericals related to junction capacitance and few more numericals on PMOS, right? Because week 1's content was primarily focused on solving more problems related to NMOS, We solved one question related to PMOS, but we will take up a few more questions related to PMOS in this tutorial session. Okay. With this brief introduction, let us start today's session. Okay, so this is the unified formula for IDS. Okay, and for the junction capacitance related questions, we will be using these two formula. So I request you guys to please note this down. Okay, and also this I leakage formula. So I'll take a 1 minute pause so that you can note down these three equations, so that we can proceed with today's tutorial session. Okay, I hope everyone has noted these formulas down. Okay. So we will start with today's tutorial session. So in the first question, okay, so we are supposed to figure out what is the threshold voltage of a transistor in which we have leakage current when VGS is equal to 0 is 10 to the power 5 times less than at VGS is equal to VTH. Okay, both at the room temperature. Okay, and it is mentioned that the VDS is same for both. We are given an information that eta ideality is equal to 1.5. Okay, so we saw the I leakage equation. Let me call it I. Okay, let's write it I leakage equals I naught exponential VGS minus VT by eta phi t into 1 plus e to the power minus VDS by phi t into 1 plus lambda VDS. Okay, and now let us use the information that is given to us. We know that the leakage current that is going to be obtained when VGS is equal to 0 is going to be 10 power 5 times less than at VGS is equal to VTH. Okay, so let me call the leakage current for VGS is equal to 0 as IL0. Okay, so IL0 equals I naught e to the power, in this case VGS is 0, so e to the power minus Vt by eta phi t into 1 minus e power minus VDS by phi t into 1 plus lambda VDS. Okay, this is my equation 1. Okay, next let me mention it that this is ILVTH to denote that this is the leakage current when VGS is equal to VTH, equal to I naught e power VTH minus VTH by eta phi t 1 minus e power minus vds by phi t 1 plus lambda vds. Okay, this is my equation 2. Okay, and it is mentioned that okay, it is mentioned that ILVTH is equal to 10 power 5 times IL0. Right, this is my third equation. So by rearranging the third equation, I can write IL0 by ILVTH equals to 10 power minus 5. Okay, is everyone with me till this point?
Yes, sir.
Okay. Okay, so these are the three equations that I am going to use to solve this numerical. I think you have got a hint about how we are going to proceed. We will just substitute the value of IL0 and ILVTH in equation number 3. Okay, so let me do that. This implies, okay, what is the equation? Okay, so if I divide equation 1 by equation 2, okay, so this is actually 1, right, because we have e to the power VTH minus VTH, so e to the power 0. Okay, and if I divide 1 by 2, then I0 is going to be cancelled and 1 plus lambda VDS is going to be cancelled, as it is mentioned that it is having same VDS for both. Okay, and the same thing is going to happen for this particular term as well, 1 minus e to the power minus VDS by phi t, because VDS is given to be same for both. Okay, so if I divide 1 with 2, then I have IL0 by ILVTH equals e to the power minus Vt by eta phi t. Okay, and from equation 3 we know that this is equal to 10 power minus 5, right? So I can write that e to the power minus Vt by eta phi t equals 10 power minus 5. Correct? Now I need to remove this e. So I'll take ln both sides. Okay, so I'll be left with minus Vt by eta phi t equals minus 5 ln 10. Okay, this implies, okay, so let me make it positive. So Vt equals to 5 ln 10 into eta into phi t. Okay, this is equal to 5 into, so eta value is already given to us as 1.5. Okay, and phi t Okay, and temperature is given to us as 298 Kelvin. So there the phi T can be taken as 25.6 millivolt. Okay, okay, into ln 10. Okay, so the answer is going to be 0.44209 volt. Okay, this is going to be our VT. Okay, is everyone clear with this question, or is there any doubt? Is this problem clear?
Sir, when you divided equation 1 with equation 2, the thing you have done with like e to the power that you have cancelled it. Can you explain that again?
Yeah, sure. Okay, so when I divided equation 1 with equation 2, okay, so which are the common terms that are going to be cancelled? I naught will get cancelled, right? And so equation 2 is basically I'm substituting VGS is equal to VTH, right? So if I substitute VGS equals to VTH in this equation, let us say, so what is going to happen is I will get a term e to the power VTH minus VTH by eta phi t. VTH minus VTH will cancel out, so it will be e to the power 0, that is equals to 1.
Okay, sir.
Okay, and the rest of the terms will get cancelled when I divide both the equations, because VDS is same for both the cases. Okay, yeah, so anyone else has any doubt? Okay, then let's proceed to the next question. Okay, so the next question, we are given that we have a short channel. Yeah, Harish. Please show the last slide. Okay, yeah, sure. Is that fine, Swagata? Okay. Okay, so can we proceed to the next question? Okay. Okay, so in the next question, what we are supposed to do is we are given a short channel NMOS device. Okay, and we have to figure out what is the threshold voltage, and we have to also calculate the ID if the other information are given to us, like VGS, W by L, VD sat n, Kn dash, lambda n, and psi s is already given to us. So the first thing that we need to do here is figure out what is the threshold voltage. And in previous week's live session, we did not take into consideration the DIBL coefficient, as it was not covered in week 1. But for this week's content, we will be considering the DIBL effect. Okay. So VTH is equal to VTH naught plus gamma square root of mod VSB plus psi s minus square root of mod psi s. Okay, so in previous week's live session, what we did is to figure out what is VTH, we were only taking into consideration the body effect, right? But we also know that there is something called as DIBL that is going to vary your threshold voltage, right? So we also need to consider the factor eta VDS. Okay, and why is the threshold voltage varying? So it is because we have a reversed bias PN junction diode, and let's say for the case of an NMOS device, so if VDS is going to increase, then that depletion region, it is going to go further into the channel, and because of which the presence of means it is easier to form the channel, right? So it is going to reduce our VTH. Okay, so it means the eta value that we are going to take here is going to be negative. Okay, so let us, okay, so VSB is given to us is equal to 0. Okay, so we can write it like this: VTH naught plus gamma square root of mod psi s minus square root of mod psi s plus eta VDS. Okay, this is 0 because we have VSB is equal to 0. This implies we have VTH naught plus eta VDS. Okay, and VDS is given to us as 1.2 volt and VTH naught is given to us as 0.45 volt. So it is 0.45. Okay, so this should be minus 0.05. Okay, so 0.05 into VDS is 1.2 volt. Can someone calculate and let me know what is the final answer? No. Yeah, correct. 0.39 is the
0.39.
Yeah. Okay, so now we have the threshold voltage. Now we need to figure out what is ID. Okay, so once we have the threshold voltage from previous week's tutorial, does anyone remember what should we do next?
VGS minus VT.
Yeah. So we will find what is VGS minus VTH. Okay, so VGS is given to us as 0.6 volt and VTH we know as 0.39 volt. So we have 0.21 volt as VGS minus VTH. Okay, and it is given to us that VDS is equal to 1.2 volt and and VD sat N is equal to 0.5 volt. Okay. So the minimum of these three cases is going to determine my region of operation. Sir, give the formula as negative. Okay, yeah. So you can. So what we need to understand at this point is this eta thing is going to be negative. Okay, so if you directly consider eta to be negative, so you can put it as minus and take the mod value of eta, that is 0.05 into VDS. Okay, so your understanding should be in this way, that if the VDS is going to increase, then the VTH should decrease. Okay, so because of this reason, the eta has to be a negative value. Is that clear?
So can you explain again?
Yeah, so okay, so let me, I think I'll draw the transistor diagram, that will be better. Okay, so we have this and this is, and we have gate terminal. Isn't eta positive for NMOS and negative for PMOS? No. Okay. Yeah. So consider this case of NMOS. Okay. So here, so VTH is basically the amount of gate voltage that needs to be applied for the channel formation, right? So if VD is going to be positive, okay, so you can see that it is basically a PN junction, right? If VD is going to be more and more positive, then it means the depletion region is going to be wider and wider.
Yes, sir.
Okay, so because of this, what is going to happen is the channel that was present here, okay, so this depletion region, after certain extent, it will start entering into the channel itself. Okay, it means that the amount of gate voltage that was earlier needed to form the channel is going to be less with increasing VDS, right? So it can be said that it is kind of decreasing our threshold voltage in a way, right? So it means if my VDS is going to increase, my VTH should decrease. Correct? So what I can say is either whatever is the extra term, okay, either I can say that that is negative, or I can say that I have some VTH naught X. Let me call this complete term as VTH naught X, okay, minus eta VDS, where eta I'll take it as a positive quantity. Okay, does that answer the query?
Yes, sir.
Okay. Okay, then so another student asked me a question in case of PMOS if VDS increases. Okay, so consider this to be a PMOS. So this will be P plus N and P plus, right? So now if the VD is going to increase, if the VDS is going to increase, then instead of reverse bias, this is going to be a forward bias, right? And because of this reason, the threshold voltage is going to increase. Is that clear? So if threshold voltage increases, and I know that my VTH naught is actually negative in case of PMOS, okay, so my eta sign is still going to be negative with VDS increasing. Is that clear? Yeah, Bhupesh.
Sir, can you explain how VDS increasing when VTH is decreasing?
No. So I'm saying that if I consider a PMOS, okay, so one of the question was that eta has to be positive for one and negative for one case, okay. But the thing is, if I consider a PMOS, if the VDS is going to increase, okay, if the VDS is going to increase in the case of a PMOS, then this junction is going to be forward biased. If it is going to be forward biased, then the depletion region width is going to decrease. Okay, and if it is going to decrease, then I can effectively say that the VTH is going to increase. Okay, so if I say for a PMOS case, I have this equation VTH not X, okay, plus eta times VDS. Okay, I know that VTH not X is negative. It's a negative number. Okay, and I say that if VDS is going to increase, my VTH should increase. It means this entire quantity should be more negative. Right? So if this entire quantity has to be more negative, what is the sign of eta?
Negative.
Correct. Okay. So this thing holds true for both the cases, that whether it is NMOS case or PMOS case, you can use this unified formula. Okay. Yeah, there's a question someone asked.
Sir, in PMOS case, our VDS will also become the negative, no?
No, it depends, right? Here I have taken a case in which I have grounded the source and I'm increasing the VD, so it means VDS is increasing. Right, I took two cases. One case I took NMOS, one case I took PMOS. Okay, in both the cases I have taken the source to be ground and I'm increasing this particular potential.
Okay, sir, got it.
Okay.
Sir, but PMOS, in case of PMOS, source is to be at a higher potential, no?
Okay.
So, sir, if in case of PMOS, source is in zero potential, and if we increase the drain potential, then in case of PMOS, source and drain should be touched because source should be in higher potential. In case of PMOS, and in case of NMOS, drain should be in higher potential.
Okay, so if we see it in that way, okay, if PMOS is there and I'm increasing the voltage here, the drain side, I will have yeah, I think that's a valid point. Okay, if the source is changed, so it means that this is the drain and this is the source. Okay, yeah, then also it is fine, right? So now if I am increasing the drain, right, means either of the terminal can be drain or source, but if I am increasing the drain potential, it means I am increasing the potential of the P terminal, right?
Yes, sir.
Yeah, so anyways it is going to increase my, means it is going to make it more forward biased, and because of which the VTH is going to decrease. Does that answer your query, Saugata?
Yes, sir. But you said in case of NMOS and PMOS, both eta would be negative.
Yeah, I mean if you
But
use
in
this like unified formula.
Okay, sir. Actually, but in case of Serre formula, there was a minus, and that's why I confused.
Oh, okay. Yeah. That was because means even in this question, if you take the minus sign here, so what I did is I combined the minus sign in the eta itself.
Okay, sir.
Okay.
And sir, we can also do it like that, na? We always write minus eta VDS and we put the VDS as per the sign. Like if it's NMOS, then it will be always positive, and if it's PMOS, then we'll put it negative.
Yeah, sure. I mean, if that is comfortable to you, you can do it that way.
Okay.
Sir, means if it is an NMOS device, then overall Thevenin voltage will decrease, and for PMOS it will increase with Thevenin voltage.
Yeah.
Yes, sir. So according to that, if minus zeta VDS was the term and zeta will take eta will take I positive, and in case of NMOS VDS is positive, so threshold voltage will reduce. But in case of PMOS VDS is negative, that means threshold voltage will increase.
Okay. Yeah, you can use that sign convention as well. I mean, whichever you find it to be comfortable. Is that clear?
Okay, sir.
Okay. Okay. So now we have the VTH and we need to figure out what is the ID. Okay. Yeah. Okay. Did I something? Okay. So here we saw that the minimum is VGS minus. Okay. The minimum is VGS minus VTH. And because VGS minus VTH is minimum, so the transistor is in saturation. So we can write ID equals half into, so it is given to, yeah, okay, someone, yeah, someone raised their hand. Okay, so here Kn dash is given to us as 200, lambda n is given to us as 0.07, psi s is 0.35, and W by L is equal to 5 lambda by 2 lambda. So we will directly put it into the equation into 5 by 2. Okay, so into, this is my VGS minus VTH whole square into 1 plus lambda is 0.07 into 1.2 is my VDS, okay, into 10 to the power minus 6 because of this Kn, okay. So we have 11.025 and into okay. Yeah. So in the previous question we considered VSB is equal to 0. But now let us consider that VSB is equal to 0.2 to take into consideration the body effect, okay. So we have VTH is equal to 0.45 plus the gamma was given to us as 0.6 square volt. So 0.6 root over of 0.2 is the VSB plus psi s is 0.35 minus square root of 0.35 0.05 into 1.2, that was our VDS, okay. So we know that if we subtract these two, then we will get 0.39 as we did in our previous question. In this one we have square root of 0.55 minus square root of 0.35 equals 0.39 plus 0.09. Yeah, so 0.48. Sorry, I lost internet connection. Is my screen visible?
Yes, sir.
Okay.
Yes, sir.
Okay. Yeah, so we have VTH is equal to 0.48. We will calculate VGS minus VTH. That is 0.6 minus 0.48 is equal to 0.12 volt. Okay. And so 0.12 volt means VGS minus VTH is still the minimum out of the three, that is VDS and VD at N, right? So it is again going to be in saturation. So to 200 into 5 by 2.
Sir, one doubt, sir.
Yeah.
So if VGS minus VTH and VD sat, if both are same values, what is the region of operation, sir?
If VGS minus VTH and
VTH and VD sat got both the same values. Suppose, for example, VGS minus VTH is equal to 0.5 and VD sat is equal to 0.5. What is the region of operation?
Just a minute, I think my call got dropped.
So your screen is not visible.
Yeah, there is some internet issue. Is it visible now?
No, sir. Yes, sir.
Yeah, so if VGS minus VTH and VD sat N both are same, it means that the transistor is just on the verge of saturation, right?
Okay, sir. Thank you.
Yeah. So the V min is anyways going to remain the same whether you consider VGST minus VGS minus VTH or VD sat min. Right, so the equation we are going to use the unified equation, and the only thing that we needed to change was the V min value, which we were going to take the minimum of the three cases. Okay, so the only thing in question was what is the region of operation. So it is going to be on the edge of saturation. Okay, to 0.12 square 10 power minus 6 into 1 plus lambda VTS. Yeah, 3.9024. Okay, so this is our question 4. Okay, so now we have a few questions related to the capacitance. Okay, so what we are given is we have a PMOS transistor whose W is 0.18 micrometer and L equals 0.6 micrometer. Okay, and gate oxide, it is the thickness of the gate oxide is 0.8 nanometer. Okay, epsilon R is given to us as 12. Okay, epsilon naught value is mentioned. We have to figure out what is the gate capacitance. Okay, so capacitance is equal to A epsilon naught ER by distance. Okay, and distance is nothing but the Tox. Okay, so our area is going to be 0.18 micrometer into 0.6 micrometer into epsilon r, that is 12, and epsilon naught, that is 8.854 into 10 power minus 12 by Tox. Tox is given to us as 0.8 nanometers. Okay, so this much farad. Okay, can someone try to calculate this? Okay, yeah, as it was mentioned for two places, so that's why till only 7.34. Okay, moving on to the next question. Okay, so we are given a short channel PMOS transistor. We need to figure out what is the mod VTHP. Can you share the please? Okay. Okay, so can we proceed with the next question? Okay, so here we are given that, okay, here eta is given equals to 0. So VTHP is equal to VTH naught P plus gamma square root of mod psi s plus VSB minus square root of mod psi s plus eta VDS. Okay, but in this case eta is given as 0, so this component is going to be 0. So this is only the VTH considering body effect. Okay, we are given that VTH naught P is 0.4, so is minus 0.4, and gamma is minus 0.4 square root of psi s. So mod psi s is 0.35, so minus 0.35 plus what is VSB? So we have VS minus VB equals 4.5 minus 3.1. Okay, that is 1.4 volt. 1.4 minus square root of 0.35. Okay, that is minus 0.4 minus 0.4 into 0.433, that is minus 0.5732 volt. Okay, now let's find out what is VGS minus VTH. VG is 1.9 minus VS is 4.5 minus VTH we found out to be minus 0.5732. So that will come out to be around okay, and VDS equals 4.4 minus 4.5 equals minus 0.1 volt. Okay, so from okay, VD sat P is not given, is it? Okay, VD sat P is minus 0.5. So out of these three, which one is the maximum? Minus 0.1, right?
Yes.
Minus 0.1.
Yeah. So this transistor is in linear region of operation. Okay. So using the unified ID equation, we can write it. Kp was given to us as 100. So 100 into 10 power minus 6 into 5 by 2 into VGS minus VTH, that was minus 2.0268 plus
Minus 100, sir.
yes, oh sorry, I forgot this, plus 0.1 by 2, okay, into 0.1 okay, so this sign is plus because 0.11 is negative and 0.1, that is VDS, is also negative. Okay, so okay, I'll cancel these two negative signs as well. So I'll have 100 into 10 power minus 6 into 5 by 2 into 0.1 into okay, this term will give us the negative, into magnitude is 1.9768 into this one is 1.011. So we have okay. Okay, so the next question, you just need to replace whatever equation we had. Okay, in that thing you just need to substitute the value of eta and again redo the calculation. So this is a practice problem for you, you can try it out. Meanwhile, we will try another question that is related to the drain diffusion capacitance, right? So this is a question from the capacitance side. This is question number 7. Okay, so we have to estimate the drain diffusion capacitance of an NMOS transistor, okay, for when drain is grounded. The area of the drain diffusion is Okay, so the dimension is given, we need to figure out the area. Assume that the substrate is grounded. Okay, so substrate is grounded means the body, they are mentioning that the body is also grounded, and the transistor has Cj naught equals 0.96 femtofarad per micrometer square, Mj is equal to 0.36, Cj S naught Sw naught equals to 0.2 femtofarad, Mj Sw equals 0.1, phi naught equals to 0.75. Okay, and we have to figure out the drain diffusion capacitance. Okay, so what is the drain diffusion capacitance? That is CdB equals to C bottom plus C side wall. Okay, that is going to be so C bottom is our Cj into WLS plus C side wall is CjSW into W plus 2LS. Okay, and here it is given to us that Vd equals to 0 and Vb equals to 0. Substrate is grounded. Right? So it means our Vdb equals to 0, which means our Cj will be equal to Cj naught. Okay, I'll tell you why. Because Cj equals to Cj naught by 1 plus Vdb by phi naught whole power m. Correct? And because our Vdb is 0, how to visualize different types of capacitance in a transistor? Yeah, okay, sure. After covering questions 7, 8, 9, we have 2 more questions, and then I'll try to diagrammatically represent where the capacitance are present. Will that be fine? Okay. Okay, so in this case it is given that Vdb equals to 0. So if this is 0, then our Cj equals to Cj naught. Okay. Similarly, for CjSW also we have CjSW naught by 1 plus Vdb by phi naught to the power MSW. Sorry, MJSW. Okay, and because Vdb is 0, so it means our CjSW is equal to CjSW naught. Okay, so now it is only a matter of substitution. So Cj is Cj naught, that is given to us as 0.96 femtofarad per micrometer square. Okay, so if micrometer square is in the denominator, so I can write it in the numerator as plus 12 into, I have W as 0.9 micro into L is 1.2 micro. Okay, and CjSW is equal to CjSW naught, so I can write it as 0.2. Okay, micrometer means I'll take the 10 to the power minus 6 to the numerator, so it will become 10 to the power 6 into the W is 0.9 plus 2 times L, so 1.2 into 2 into 10 power minus 6, because the micro is present, so 10 power minus 6, 10 power 6 cancelled, 10 power minus 6 and 12 will get cancelled, so we will be left with 0.9. Is this question clear?
Sir, please explain how this W plus 2LS.
Okay. So this W plus 2LS I'll diagrammatically explain after we complete the remaining two questions. Will that be fine?
Okay, sir.
Okay. Any other question related to this one? So the diagrammatical explanation I'll do after question number 9. We have only 2 more questions left. So
if you consider sidewall capacitance,
sidewall capacitance of?
in this one, actually ignore the gate sidewall capacitance. Suppose you want to consider this one.
Okay. So gate sidewall capacitance is usually ignored, right? So that thing appears with the channel itself. So that's why we don't usually take into consideration.
Okay.
Okay. So let's proceed with question 8. Okay. So now, so in earlier case, what was given to us is VD is equal to 0 and VB is equal to 0 because both were grounded. Okay, so we did not see because of the presence of body effect how the CJ was CJ was affected, right? Just a minute. Okay, but let us try to do this particular question. So it is given to us that VDB equals 0.6 minus 0.2 is equal to 0.4. Okay, in the previous question, because VDB is equal to 0, so CJ was equal to CJ naught. Okay, but in this question we need to consider CJ. We need to calculate CJ. Okay, so CJ is equal to CJ naught by 1 plus VDB by phi naught whole to the power m. Okay, so that is going to be 0.96 femtofarad per micrometer square by 1 plus 0.4 by phi naught was given to us as 0.75 and mj was given to us as 0.36. Does anyone have a question? So I request the participants to please mute themselves. Please mute yourselves. Okay, previous slide. This one? Okay, is that fine? Should we proceed to the next question? Okay, so phi naught was given to us as 0.75 whole to the power m. So the value of m was mj was 0.36. Okay, so this is going to be Yeah. Similarly, we also need to calculate what is our CJSW. Okay, so CJSW is equal to CJSW naught by 1 plus VDB by phi naught whole to the power MJSW. Okay, this is 0.2, I think. Yeah, 0.2 by CJSW is 0.1916. Okay, let's see. 0.4 by 0.75 whole to the power 0.1, 0.19. Yeah, it is 0.192. Okay, so we have the CJSW value with us. We also have the CJ value with us.
Sir, last one will be per micrometer.
Oh, sorry. This is, yeah. This is sidewall, so it will be per micrometer. So we have CJ with us. We also have CJSW with us. So similar to how we solved this question, okay, we just need to substitute the value of CJ and CJSW here. Okay, and then we can figure out what is the CDB. Okay, is that clear? Or is there any doubt here? Okay. So I'll take a 1 minute pause at this slide. So if anyone has any doubt apart from the diagrammatical representation, so they can let me know. Okay, so let me tell you what we did. So here we were supposed to figure out what is the drain diffusion capacitance. Okay, and drain diffusion capacitance is the summation of your bottom plate capacitance and the sidewall capacitance. Okay, and that turns out to be this. Okay, how it turns out to be this, we'll get to know. So it is covered in the lecture, but I'll revisit that part again. Okay, and the next thing that we need to do is what is the value of CJW that we need to compute. In the first case, CJW was equal to CJW naught because it was given that VDB is equal to 0. But in the second case, we changed the value of VD and VB and told to recalculate what is CJ. Because in this case, CDB is a non-zero value, so our CJ had a different value in comparison to CJ naught. We figured out what is that CJ value, what is that CJSW value, and based on that, we need to repeat this calculation, okay, and just substitute CJ and CJSW with their respective values. Okay, that's all we did. Okay, so I think these things should cover your capacitance related problems. I mean, these are kind of in similar lines to what is asked in your assignment, so it will be helpful for your assignment. So someone asked me to solve this capacitance related problems last time, so this is where it is. So the next question is actually a bit modified version of what we have solved earlier. So can someone tell me how to proceed with this problem? Can solve on leakage current problems. Actually we did one problem related to leakage current, right? So rest of, like, most of the other problems are just simple variation of that. Okay, can someone tell me how to proceed with this? Gate capacitance equals Cox times A. Okay, but Cox is not given to me. Like, can you be a bit more specific?
Cox is equal to epsilon naught divided by TOX.
Correct. Okay, so it is going to be similar to the problem that we solved before, 3 questions. So C equals to epsilon r into epsilon naught into the area, that is 0.36 into 10 power minus 6 into 0.18 into 10 power minus 6 by Tox, that is 4 into 10 power minus 9. Okay, and this will be, so did anyone calculate this? Point 237. Yeah, it comes out to be around 0.56 femtofarad. Okay, now let me so these were the set of questions that I thought of solving for today. Now let me go for the diagrammatic explanation of the
Sir, I have a query.
Yeah, sure.
Nothing much, sir. The relative permittivity of oxide is 3.9. But in the assignment, they've given it as 12.
Yeah, actually, so that's a
mistake.
No, that's not a mistake. That is correct, because in this question it is mentioned that it is hafnium oxide. So we have something called as high K and low K dielectric, right? So basically, as in one of the lectures that sir mentioned, that when we go down decreasing the when we go into higher technology nodes, right? So means ideally we expect that the current through the gate will be 0, but as we proceed going on into higher technology nodes, so we see some quantum effect coming into picture, and because of that there is certain amount of current that flows into the gate. Okay, and because of that, so high K dielectrics are used, and yeah, so high K dielectric, so it is 12, that is correct. And yeah, so this is normal dielectric, that is 3.9. Normal dielectric is your silicon dioxide. Okay, so let me go to the picture. Okay, I'll add one more slide. All recorded problem solving session are uploaded at that link. Yes, so I think NPTEL team has shared an Excel sheet with you, right?
Week 1 video is uploaded, sir.
Yeah, week 1 video is uploaded. So this is week 2's video that will be uploaded, I think. Otherwise, I'll upload the recorded this particular today's session by 8:30. So I mean, you can check that session here in this channel. Yeah, only week 1 is uploaded because week 2 is conducted today, right? So once I end this session, after that the week 2 content will also be visible to you. Okay. So now moving on to our diagrammatic representation. Let me add One more slide. Insert new slide. Okay. So I'll start from the front view and top view part. Okay. So the diffusion region, it will appear something like okay. Now, so for the CDB, okay, what we wrote is CBOT plus, okay, just a minute, C sidewall, okay. So your question was, how was it W plus 2LS, right? So this sidewall capacitance is nothing but the capacitance that is arising because of the perimeter, right? So let me take this one into consideration. Okay, so let us assume this shape is not like this and it is something like this. Can we do this approximation? Okay, and we know that the dimension of this thing is LS and this thing is LS and this thing is W. So what is the perimeter?
W plus 2LS.
Yeah, you just take the summation of all the sides, right? So we have W plus LS, that is W plus 2LS. Okay.
So
now,
why not the other W?
This side is, are you talking about this side?
So in the other diagram where you have converted the semicircular into.
Okay, this one. Yeah, because if you consider one as drain, the other one will be the source, right? So that is CSB. Okay. Okay, so we have the total perimeter as W plus 2LS. Okay, now let me define a quantity called as CJSW, which tells us that what is the capacitance per unit length. Okay, so if CJSW is my capacitance per unit length, my total capacitance will be capacitance per unit length into total length or the total perimeter, right? And I know my perimeter is W plus 2LS. So I have CJSW into W plus 2LS.
Sir,
Yeah, Harshit.
sir, here you have taken W plus 2LS. So LS is the source length basically. But in the question, it was given the channel length, not the source length. So why we have used that channel length?
I don't think channel length is given. Is it given like channel length? No. So L is the diffusion
Basically,
length.
L is the okay.
So okay. So channel length, it won't be possible, right? Wait. Yeah. So channel length is this one, right?
But in current equation, I think this length is
Yeah,
already
that is
used.
in current equation.
Okay, so the given length in the question is not channel length.
Yeah, that is not channel length. That is this particular length of this. Okay, we actually denote it as LS. Okay, and this to this is called as a drawn length, LD. So don't get confused between the two lengths. Okay. So while solving the capacitance, just remember that we are talking about this length and not the channel length. Okay. Okay, so yeah, these were the questions that I thought for today. The recorded lecture will be available after 8:30. Once this session closes, I'll save this thing and I'll upload the recorded lecture, and I'll also leads to increase in VTH. Okay, yeah, sure. So as I mentioned that, okay, so if we are going to increase this, let me call this as VD, okay, and this is my N plus and this is P. Okay, if I go on increasing the VD, what is going to happen is my depletion region is going to increase, right? And my problem is the diffusion region is actually entering into the channel. Okay, if it starts entering into the channel, it means it is basically forming the channel, which was supposed to be formed only after a particular gate voltage is applied, right? So when I use an implant, let's say I use a P plus implant, what happens is instead of the diffusion region, instead of entering deep into the P region, it starts entering a bit into the N plus region more. Okay, so the effective entry into the P region, it decreases. So now it becomes something like this. Okay, it means, so we have successfully avoided that particular penetration into the channel. Instead, it is now penetrating into the N plus region. Correct. And because of this region, now the VG that needs to be applied for the channel formation is going to be a bit more in comparison to the one where this P plus implant was not used. Okay, does that answer your question, Tarun? Okay. Yeah, Shilpa, sure. I'll upload the video. So last time actually there was a few, there was a bit of delay and it got uploaded at 9 p.m. That was because of slow internet, but I think today it should be fine. I'll upload it at 8:30. Anyways, you guys also have the link to the sheets, right? So this one will be this particular slides. These will be uploaded on the Google Drive. You guys have access to that, right?
Yes, sir.
Okay. Sure. Is there any other doubt that you want to discuss?
Sir,
Yeah.
Sir, in this case where you have told us about the P plus implantation, there if we do this, there will be increase in VTH now.
Yeah. So there will be increase in VTH, but because of application of VDS, the VTH was going to be decreased, right? So in a way, we wanted to cancel this decrease in VTH with increase in VTH. Okay. So net effect is we want the VTH to be constant. It should not be much dependent on the VDS. Okay, so let us revisit what we did today. So in today's session, what we did is we tried to incorporate one more short channel effect, that is DIBL, into our VTH equation, and we tried to solve for VTH. The first question was related to leakage current, okay, and it is mentioned by what factor. Any book for these topics, Jan Rabe will be a good one. I think the complete name of the book is Digital Integrated Circuits by Jan Rabe. Rest, I think sir's lectures are good enough. Okay, so they go from a very fundamental level. And so week 1 and week 2 we had focused primarily on the device side of things. Okay, from week 3 onwards we will go deeper into the digital integrated circuits part, starting with the inverter. I think GIDL was not, it was just mentioned that there exists a point called as a GIDL point when we are going on decreasing this thing, but it was not it was not discussed in detail in the lecture, and that is also something that I think more into the device physics side. So we as designers, we just need to know that such a point exists, okay, like while considering that sub-threshold leakage topic. So yeah, I think only the point matters, and otherwise we will need to go deeper into the device physics side. And yeah, okay, so in the first question we did something related to the I leakage, okay, and here, so this factor here we took as 10 power 5. So it can be anything, but the procedure for solving this these type of problems will remain same. Okay. So the next question we did was related to the DIBL coefficient. Okay. So we took that into consideration while solving for VTH. We solved for VTH. Then we did our the regular methods that we used to do. Out of the three, VGS minus VTH, VDS, VDSAT N, which one is the minimum? That will determine our region of operation, and based on that we will get our Vmin, and from that Vmin we calculate the ID. Okay. In the next question, what we do is we assign some value to VSB, so that we take the body effect into consideration as well, because in the previous case we had VSB is equal to 0. Okay. So with VSB, VTH changes, and again we redo the same thing. Okay. In the next question, what we did is we had to estimate the gate capacitance. We were given the W and L. Okay. And we were supposed to figure out what is the gate capacitance. Epsilon R was given to us. Okay. And based on that, Tox was also given to us. So based on that, we calculate the capacitance as A epsilon naught into epsilon R by Tox. The next question was related to, okay, someone is joining now. The next question was related to short channel PMOS transistor, and we were supposed to calculate the VTHP in that case. So VTHP we found out to be this much. So mod VTHP is magnitude of this one. If if we, in question number 6, DIBL coefficient for PMOS is positive or negative. If we take, okay, what was the complete? If we take positive eta VDS in the unified current formula, yeah. So we have to take eta is equal to minus 0.04. Okay, so in the unified formula, you just substitute that and you can solve for it. Okay, in the next question, the drain diffusion capacitance of an NMOS transistor is given to us, and we were mentioned. Okay, so as someone said that he was confused with this one, so let me write it as LS. Okay, so this should be LS actually. Okay, so it was given to us that drain and substrate both was grounded. So substrate is nothing but the body. So try to see for these kind of hints in your question. And it is mentioned both body and drain are grounded. So VDB is equal to 0. And when VDB is equal to 0, you can directly take CJ naught as your CJW. And you can also take CJ SW naught as your CJ SW, right? Because here this term vanishes because VDB is 0. Okay, so this is one question, and we saw how this particular formula was derived and how this perimeter was W plus 2LS. It was demonstrated in the diagrammatic part at the end. Okay, so in this case we need not calculate CJ, but if it is given that VDB is not equals to 0, then we need to figure out what is going to be my CJ. That is what we did here. Okay, and then we just need to substitute these values in that CDB equation. And question 9 was similar to the question that we did earlier. That is A epsilon naught epsilon r by d. Okay. Yeah, so I think that's the end of today's session. If anyone has any doubt, please let me know. Wait, this is LT. Okay. Okay, so does anyone have any doubt in the week 2's content? So these recordings will be uploaded and I think you guys already have the sheet from NPTEL team that contains the lecture slides location and the link for the uploaded lecture. So I'll be around for a few more minutes, so let me know if anyone has a question. In brief, how VTH decreases when VBS is applied. Okay, so observe this transistor. Okay, so let us say there is another terminal. This is VB. Okay, and this is my VG. So can you tell me what happens when VG is applied here at the gate? Correct. If let's say VG, I'm taking it, okay, let me call it as VGS. Okay, so if VGS is greater than 0, right? So it means that the channel formation starts when VGS crosses a particular threshold, right? So imagine the body, the VB, to be acting as another gate, okay? And that gate is actually helping you in this channel formation, okay, by increasing the amount of the minority carriers that will be present there. Okay, so if it is going to increase the amount of carriers that will be present here, it means that it is going to help you in the channel formation. Okay, and if something is going to help you in the channel formation, it means the work left for the gate to be done is going to reduce. Okay, so in other words, we can say that the VTH is going to reduce. Okay, so that's why this thing is also called as a backgate effect. Okay. Yeah, is there any other question? So, so I wanted to know, is the pace of this lecture, this tutorial session fine, or should I be a bit more slow? And is there any other feedback that you want to give?
It is fine, sir.
Okay, okay, sure. Okay, then if anyone else has any question, and I hope whatever we solved today, right, it will be helpful for your assignment questions, and also it will be helpful for your exam. So yeah, okay, so I think the deadline for assignment 2 is tomorrow, right? I'm not sure.
Yes, sir, tomorrow.
Okay, okay, so I think yeah, you can revisit both week 1 and week 2's content, and you can try solving the assignment problems, and if you have any doubt, you can let me know. And so yeah, before coming for the next week's tutorial session, so you can go through the week 3's content. So in next week's tutorial session, we will be covering week numericals related to week 3 and your assignment 3. Okay, so yeah, Ajit. Yeah, sure, Gopal.
Actually,
Yeah.
sir, in the form of BH, we use minus equals or plus eta.
Sorry, can you repeat?
Sir, in formula of BH, we use minus or plus BH.
Where?
We give the formula minus eta VDS.
Okay, minus eta VDS. It is based on your convenience. So I write it as plus eta VDS, and so you just need to figure out what is going to happen to your VTH if your VDS increases.
Sir, means our VTS should decrease. If VDS increase.
Yeah, if it is a NMOS, yeah, true.
Sir, in PMOS also it should be decreased now, but in negative value by taking the sign.
Yes, correct. So if it is going to be in negative value, it means if it is going to be more negative, then it means this particular sign should be negative, right?
Yes, sir.
Yeah. So
sir, I solved the tutorial by using minus eta VDS, not taking plus eta VDS.
okay, but you must have taken eta as negative, right?
Yes, sir, I take the eta as negative.
Yeah, okay, then that is correct.
Okay, sir.
Yeah. Okay. Is there any other question? Yeah, Gopal, I'll upload the recordings right after this session ends. So Yeah, you can maybe check around 8:45 or 8:30. It will be available on YouTube, I think. Okay. Is there any other question? Okay. If not, then we can wrap up today's session. Okay. Thanks everyone for joining.
Thank you, sir.
Yesterday's session recording, I'm not sure. So, who is taking yesterday's session?
Sai Shubham, sir.
Okay. I think then he will upload it because I don't know him. Okay. Okay. Thanks everyone.
Thank you, sir.
Thank you.
Thank you, sir.
Thank you.